Hello and welcome to a presentation on exact graphs for economics exercises and exams. How economists can combine old tools, graphs, and technology, machine-generated plots, to design better exercises and exams. In this video, I will rewrite an intermediate microeconomics exercise. I will present a familiar example of a canonical intermediate microeconomics exercise and later show how it can be rewritten and improved using the graph-first approach. I will go through it progressively so you do not need to read it all now. This is a real exercise on the tragedy of the commons assigned in May 2026 during an in-person exam at a Scottish university. Students had about 20 minutes to solve it. First, the exercise asks students to define the tragedy of the commons. Then it asks them to solve a model featuring that concept. Definition and solving are separated. The definition comes before the model is even introduced, so students provide a context-free definition disconnected from the exercise. Students then spend most of their 20 minutes solving the model and computing outcomes. In questions 2, 3, and 5, they solve for the number of cows under free entry in a social optimum, for profit levels, and for an optimal license fee per cow. Question 4 asks students to illustrate results on a diagram after they have already solved for key outcomes. The graph is unnecessary for solving the model. Its sole purpose is reproducing the textbook graph and inserting numbers, such as the intercept of 26,000, the price per cow of 2,000, social optimal level of 6 cows, free entry equilibrium with 12 cows. The exercise adds nothing else to the textbook. There is no novelty and little intellectual payoff. I will now show how to rewrite and improve the exercise by following a graph-first approach. The instructor solves the model first and provides a finished graph. The graph, like variance, plots the number of cows on the horizontal axis, output per cow on the vertical axis. The price of a cow will be added later. The graph is exact and machine-generated, optimized for precise reading. The last thing to note is I assume a different functional form, introducing a nonlinearity. I will return to that point. The rewritten exercise begins similarly, but introduces a model immediately. Consider a commonly owned pasture. Villagers can purchase cows for $1,500 each, graze them on the pasture. When there are C cows, total output is F of C. Students receive the graph at the outset, and the first question focuses on interpreting it. Which curve represents marginal private benefit, which curve represents marginal social benefit, and what a vertical distance between them represents. The average product corresponds to marginal private benefit. A farmer adding 1 cow receives the average output from that cow. The marginal product corresponds to marginal social benefit. The difference between the two, average product minus marginal product, is a marginal external damage, a negative externality. For example, when the 190th cow is added, the farmer receives 3,505, while total output increases by 2,250. The difference is a negative externality imposed on all the existing cows. Hence, this first question engages students with a graph and introduces a model using the language of externalities rather than requiring a generic definition. The exercise then proceeds just as before the rewrite. Students have to determine how many cows will be grazed under free entry and the resulting profit, and they are expected to show that farmers will add cows until the marginal private benefit equals the marginal cost. The cost is $1,500. This leads farmers to add 476 cows, and all profits are dissipated, zero profit. Next, the socially optimal number of cows is found by equating marginal social benefit with marginal cost. This occurs at 246 cows. The profit from the socially optimal number of cows can be computed in 2 ways. One way using the average output, alternatively as an area between marginal social benefit and marginal cost. Finally, a license fee can be used to decentralize the social optimum. By increasing the price per cow, we can induce farmers to stop at 246 cows, internalizing the externality. The required license fee is $1,687. The exercise is now complete. I will now explain the advantage of the graph-first rewrite by outlining the key selling points. Selling point 1 is efficiency. Since lectures use graphs, exams should do the same. That continuity removes the need to translate between algebra and diagrams. Answers have become numerical and notation-free. For example, the socially optimal number of cows is 246. Profit is 415,000. This works very well for online quizzes. Alternatively, students can record their answers directly on the graph, making their answers compact and making grading more efficient. Selling point 2 is what I call the outsourcing of solving. Notice that the graph itself performs all the computationally difficult steps. Instead of algebra operations, we have something simpler, finding intersections. Students obtain results by reading the graphs, and all they have to do on top of the graph is performing basic arithmetic. They can solve the entire exercise with the graph and a pocket calculator, even though the graph first rewrite introduced a nonlinearity. Graphical methods are simply more powerful than algebra for two-dimensional problems, and outsourcing the solving allows instructors to let students use more powerful methods, reducing the amount of mechanical work. The value of outsourcing the solving is probably better illustrated through another example. Here we have a graph representing two household types, each facing a consumption and leisure trade-off, two tax and transfer schedules, with budget balanced redistribution, and kinks in the budget constraints. Solving this model with pen and paper is near impossible. On the other hand, I have assigned this exercise to undergraduates, because the exact graph outsources the burden of computation to the instructor, while encoding the solution efficiently. Students can use the graph and answer simple questions to show that they understand the model without spending much of their time on algebra. The third selling point is a novelty. In this example, I departed from the textbook model and graph by making the externality only appear after 86 cows. This can be the basis for meaningful interpretation questions connected to cow density on a pasture. I now turn to another reason to introduce this nonlinearity. As you can see here, it is perfectly possible to do a graph first rewrite of this problem and keep the linearity, and the solution would proceed normally. With these numbers and a price of 1,500 per cow, we would find a social optimum of 160 cows and a free entry equilibrium with 320 cows. The problem is that there are now linearity artifacts, such as the number of cows in the free entry being exactly twice the number of cows in the social optimum, as well as another relationship whereby the profit from the first cow is twice as much as the optimal license per cow that would decentralize the social optimum. These linear artifacts are unavoidable. They're also not economically meaningful. These artifacts can lead to students interpreting bogus results. It can also lead to students having correct answers derived from incorrect reasoning. By contrast, in the nonlinear graph-first rewrite, correct answers cannot happen by accident and require correct reasoning. Finally, the last selling point is multiple variants. Multiple versions of the same graph can be generated easily by changing parameters. This enables instructors to vary the problem across different students, which in turn provides some resiliency against collusion, or if students have access to AI tools, the increased computational complexity of the nonlinear model encourages students to interact with the AI as a tutor rather than passively rely on the AI to produce answers like an oracle. In conclusion, the graph-first rewrite improves the standard intermediate microeconomics exercise, works by being centered around an exact graph. This enables better exam design, reduces repetition, increases resiliency to collusion and AI use, while at the same time reducing the computational burden on students. These ideas apply fairly broadly. Exact graphs can be used to efficiently encode information in many areas of economics, including macroeconomic dynamics, game theory. Outsourcing computation in general allows students to focus on understanding rather than algebra and mechanics. Thank you.